students, today we are going to discuss about the next topic related with the chapter, that is, you can see in the board, that is the eddy current. So the definition, as you can see on the screen, the definition goes like this: the induced circulating current produced in a conductor itself due to change in magnetic flux linked with the conductor are called as eddy current. Now what does this suggest? This means that this is similar to the induced current only, and everyone knows that how does the induced current is produced. It is produced by the change in magnetic flux. This is also an induced current. Okay, this is also an induced current. When we change the magnetic flux, the induced circulating current, okay, induced circulating current produced in a metal, that is called as a eddy current. That is only the difference. This is a circulating current. Now based on this, I will be giving you an example, experimental proof how does the eddy current is produced. Before going to it, some examples for the eddy current, where it is used. Like we have the induction furnace. Everyone knows about the induction furnace. Everyone has in their home also. Then we have the electric brakes in trains. Then we have the speedometer in the bikes or the cars. Okay, these are all working on the principle of the eddy current. So we'll be discussing about the eddy current, its experimental proof. This experimental proof experiment is called as the jumping disc experiment. Jumping disc experiment. So how does it work, you see, this jumping disc experiment? Suppose if I consider this as one tin. Okay, we consider this as a tin which has a lid above it. Lid means if you consider one, okay, like suppose this is one tin. This is one tin. This is a lid above it. This whole tin is a metal. So what I will be doing, this tin, the lower part of the tin is connected with a wire. As you can see in the coil, it is coiled with a source. Okay, it is coiled with a source. This S is your source. This is your key, and the above lid, the lid that was there, like suppose this is the green part, the lid that is present there, the lid is just put above the tin. Clear? Now how does it work, you see? So when the current flows to the tin, we know that according to the clock rule, जिसे हम लोग ने clock rule पे already discuss किया था कि अगर current anti-clockwise direction पे flow करता है, then that pole will be behaving as a south pole. Sorry, north pole. And if it is in a clockwise direction, then that will be your south pole. Anti-clockwise, north pole, clockwise, south pole. So suppose if I consider that the current is flowing in this direction, that means it is flowing in a anti-clockwise direction in this loop. This is nothing but a solenoid only. So in this loop it is flowing in an anti-clockwise direction. So obviously this part of the coil, since it is flowing anti-clockwise, so this part of the coil it will be north pole. Okay. So if you consider here, I am showing it again. So this is, suppose this is your tin can. Okay, this is a tin can. The tin can here. Okay, the tin can here. It is current is flowing in this way. Okay, the current is flowing in this way. So this part will be behaving as a north pole, the lower part will be behaving as a south pole. Then according to the Lenz's law, the lid that was present above it, okay, the lid that was present above it, the lower part of the tin can, okay, this lid, what it behaves, you see, according to the Lenz's law, it always tries to oppose the motion of a material or a magnet. That means this lid that was present here, because it is a metal, the lower part, since it is behaving as a north pole, so this will be behaving as a north pole, and this lid will be repelled by the solenoid. But as soon as it moves upwards, then again according to the Lenz's law, the lower part of this lid, again it will be acquiring what? It will be acquiring the south polarity. Why? Because it will be always opposing the motion of the magnet. So when it moves upward, lower part will be north pole. When it moves downward, so the lower part will be south pole. Okay, so that means if you move away north pole, then it again becomes south pole, so it will be moving in this way. Okay, so this lid that was present above this tin can, so this will be jumping on the tin. Okay, so therefore this is called as a jumping disc experiment, and the current that will be produced on this lid part, that will be a circulating current. So therefore this is called as a eddy current. Clear? So this is related to the eddy current. So the next topic that we are going to discuss now is about the self induction. Now what does the self induction states? So the topic is self induction. Now what does the self induction suggest? So self induction, suppose we have an inductor. We have an inductor which is connected to, suppose in source, like suppose an AC source also is connected. Okay? The inductor, when we switch on the battery or switch on the AC source or DC source, any source that we connect, so as soon as you switch it on, the current will be flowing through this inductor. Okay, the current will be flowing through this inductor. So this inductor has a certain property that when the current flows through the inductor, it does not allow the current to reach to the peak value as soon as you switch it on the battery. ठीक है, जब बैटरी को स्विच ऑन करोगे तो स्विच ऑन करने के immediately वो डायरेक्टली पीक वैल्यू पहुंचाने नहीं देता है. That is the main working principle of the inductor. ठीक है, वो क्या करता है, वो धीरे धीरे करके करंट का वैल्यू को वो चेंज करता है. This inductor. Okay, that means this inductor opposes to the current. It does not allow the current to reach to the peak value. The resistance that is offered to the current by the inductor, this is called as a self-inductance. This is similar to the resistance. Resistance offers opposed to the current flow. The same way here also it behaves. Each and every device has its own resistance. So this inductor has also its own resistance, which we call as a self-inductance. Clear? So the definition, as you can see on the screen, the self-induction is a property of a coil by virtue of which it opposes the growth or decay of the current flowing through it. So this is your self-induction. Now suppose if a I current flows through the coil at any instant, if a I current flows through the coil at any instant, we know that if the current changes, then there will be change in magnetic field, and if there is change in magnetic field, there will be change in magnetic flux also. So we can write phi is directly proportional to your current. More the current changes, the more the magnetic flux will change. If I break this proportionally symbol, I have to write a symbol L into I. So it will be, I can write as phi is equals to Li. This L is called as self-inductance. Okay, this L is called as a self-inductance. And if I want to calculate the formula of this L, according to the Faraday's law, it suggests that induced EMF is equals to minus of d phi by dt. That was the Faraday's law. If I put a value of phi here, so it will be minus of dLi by dt. Okay, so it will be minus dLi by dt. So this L is constant, as we already know. So L will come out. So it will be L di by dt. This is the formula for the induced EMF related with the self-inductance. Okay, so in the next class, what we'll be doing, we'll be calculating the formula of this capital L. Is it clear? So any doubt related to this, you can ask me. So this much for today. We'll be continuing in the next class. Thank you.